Okay, let's dive in. We're cracking open a pretty fresh paper. This one started for ICLR 2025. It introduces a new reinforcement learning approach called drama.
That's right. And what we want to do in this deep dive is really get under the hood of drama. What are the core sort of technical ideas here, especially in model-based RL? What's new?
And how does it help you, the listener, understand where things are going?
Exactly, because, RL agents can do amazing things. We've all seen the headlines, games, robotics.
Right, but the cost often is just enormous amounts of data. They need, well, millions, sometimes billions of interactions to learn anything useful.
And that data requirement is a massive hurdle. Think about it running a physical robot millions of times just for one task. It's often just not practical.
Exactly. So the big successes you hear about, like AlphaGo or the Atari game players from DeepMind, they often use what's called model-free RL.
hmm Model free means they learn the policy, the what to do next part, directly from trying things out and seeing what works. Pure trial and error, essentially.
But that trial and error is exactly why they need so much data, right? They're basically learning patterns from scratch across countless experiences.
Precisely. Which brings us to the other main approach, model-based RL. This takes a different route.
Okay.
Instead of just learning actions, the agent first tries to learn a model of the world.
A world model, like its own internal simulator.
Exactly. It learns to predict, given where I am now and the action I take, what state will I be in next, and what reward will I get.
Ah, okay. And the big promise there, the reason people are excited about model-based, is sample efficiency.
That's the goal, sample efficiency. If your agent has a good simulator, it doesn't need to constantly interact with the real world. It can just imagine scenarios, train its policy on these simulated artificial experiences.
Practicing in its imagination.
Right, and that cuts down dramatically on the real world data needed. That's huge for making RL applicable in more places, situations where real data is expensive or slow or even dangerous to collect.
Makes sense. But, oh, I feel a but coming. There's always a catch in RL research, isn't there?
There definitely is. The big catch here is learning an accurate world model. That's really, really hard.
Especially early on, when it hasn't seen much.
Exactly. Early in training, the model's based on limited data, so its simulation is bound to be flawed, sometimes badly flawed. And if you train your agent's behavior based on a wrong simulation, well, you learn the wrong things.
So you get suboptimal behavior, and spotting why the model is wrong is tricky.
Very tricky. Detecting and correcting those errors in the learned model is a central challenge for the whole field of model-based RL.
Okay, so building these world models, especially for complex stuff like games with visuals, requires understanding sequences, right? How things unfold over time.
Absolutely. That's where sequence models become critical. They're the core component that tries to capture how the environment changes step by step.
And historically, we've seen a couple of main types. There are the older recurrent neural networks, RNNs, like GRUs.
Yep, RNNs, GRUs, they process sequences one step at a time, which is good for efficiency. Their compute and memory usage scales linearly with how long the sequence is. We call that ON.
Linear scaling. That sounds good.
It is efficient. The problem, though, is memory. They notoriously struggle to remember things from far back in the sequence, the whole vanishing gradients issue. So capturing long-term dependencies is hard for them.
Okay, efficient but forgetful for long sequences. Then more recently, we got transformers.
Right, transformers really changed the game, especially in language, with their attention mechanism. They are fantastic at connecting information across very long distances in a sequence. They solve that long-term dependency problem.
But there's that but again.
Always. For world modeling, where you might need to simulate hundreds, maybe thousands of steps ahead, the standard transformer attention mechanism has a major drawback. Its resource needs scale quadratically with sequence length.
Quadratic. So if the sequence gets twice as long, it needs 4 times the memory and compute.
Roughly, yes. That other scaling is brutal for long sequences. It becomes incredibly computationally expensive, and very quickly you run into out-of-memory errors on typical GPUs if you try to model really complex long horizon environments.
Okay, so RNNs are linear but forgetful. Transformers remember but are quadratically expensive for the long sequences we need. And this is exactly the problem drama's trying to solve, with a different kind of sequence model.
That's the core of Drama's first big innovation, yes. It doesn't use an RNN or a standard transformer. It uses state space models, SSMs.
State space models. Okay, what are those?
SSMs are a different mathematical framework actually inspired by classical control theory. They're specifically designed to model long sequences efficiently, and crucially, they do it with linear complexity.
like RNNs, but hopefully better at remembering. And the paper specifically uses Mamba.
Yes, Mamba, and specifically Mamba 2, are recent, very competitive SSM architectures. They've been challenging transformers in lots of areas because they offer that linear scaling without sacrificing the ability to capture long dependencies, at least on many tasks.
And Drama is the first time someone's built a model-based RL agent using Mamba, particularly Mamba 2, as the core of its world model. That feels significant.
It really is the central technical contribution here. By using Mamba 2, Drama aims for the best of both worlds. Efficiency, like RNNs, and the long-range dependency modeling that made transformers so powerful. This combination is potentially key for building world models that can actually handle complex, long-running simulations.
Okay, let's unpack the architecture a bit. How does Drama actually use Mamba to predict the future? There's a diagram in the paper, figure 1.
Right, so first you have the observation, maybe an image from the Atari game. This goes into a variational autoencoder, a VAE.
Okay, the VAE's job is compression.
Pretty much. It squishes that complex image down into a much simpler, compact representation, a latent vector. It's easier for the sequence model to work with this compressed form than raw pixels.
Got it. Feature extraction, basically. What happens to that latent vector?
That latent vector, plus the action the agent took, gets fed into the main sequence model, which in Drama is the Mamba 2 block.
Okay,
This Mamba 2 model takes this sequence of state, action, pairs and processes it. Using its internal state space mechanism, which remembers past inputs, it calculates what the paper calls a deterministic state. Think of it as Mamba's running summary of the situation based on the sequence so far.
and you mentioned Mamba 2 is different, somehow more efficient than the original Mamba?
Yeah, that's one of the technical points. Mamba 2 uses a clever reformulation. Instead of a purely recurrent update like normal 1, it leverages matrix multiplication with special structured matrices, semi-separable matrices. This, plus a multi-head technique, somewhat analogous to transformer attention but designed for efficiency, makes it run faster on GPUs while keeping that O scaling.
So it's fast in practice, Mamba 2 processes the sequence, creates this deterministic state summary. Then what?
That summary, the deterministic state, is then fed into a couple of simple, small prediction networks linear heads. One head predicts the reward you'll get in the next step, and the other predicts if the game episode is going to end, like if you died or won.
Okay, VAE compresses, Mamba processes the sequence, linear heads predict reward, and done. So how does this Mamba setup speed up the imagination part, the simulating future steps?
Right, the imagination phase is where you repeatedly use the world model to predict the next state, then the next, and so on. Mamba's structure helps here because the way it updates its internal state during inference when you're just running the model forward to predict is computationally very efficient and doesn't fundamentally depend on how long the sequence has already gotten.
Oh, okay.
It can just keep rolling forward relatively cheaply compared to architectures with more complex sequence-wide dependencies at each step. This significantly speeds up imagination, which is often a major time sink in model-based RL training.
Okay, so Mamba provides the efficient engine for long sequence modeling. That's innovation number 1. But we still have that nagging problem. The model might be inaccurate, especially at the start. How does Drama deal with that?
Right, and that shades to Drama's second key innovation, something they call dynamic frequency-based sampling, or DFS.
DFS, okay.
It's a new sampling strategy, and it's actually quite straightforward conceptually. It's designed specifically to reduce the negative impact of training your policy on potentially bad predictions from an imperfect world model.
Dynamic frequency-based sampling. How does it work? What's it sampling?
It looks at the transitions stored in the agent's memory, the replay buffer, these chunks of experience. Current state, action taken, next state observed, reward received. For each one of these transitions, DFS keeps track of two numbers.
2 counts for each transition.
Yeah. Count 1, let's call it V for visited by world model, tracks how many times this specific transition from the real data has been used to train the world model. Count 2, call it B for used by behavior policy, tracks how many times this transition has been used as the starting point for an imagination rollout to train the policy.
Okay, V is world model training count. B is policy imagination start count. What's the logic then? How do these counts affect sampling?
The core idea is this. If a transition has been used to train the world model more often than it's been used to start policy training, so if V is greater than or equal to B, what does that suggest?
Maybe the world model has seen this part of the world enough to make decent predictions from here.
Exactly. It suggests the world model has had a good amount of supervision from real data around this point, so it's probably more reliable. In this case, DFS increases the probability of selecting this transition as a starting point for imagination.
And conversely, if V is low compared to B.
If V is less than B, it might mean the world model hasn't learned the dynamics here very well yet. Or maybe it's even overfitted to the policy's current, possibly flawed actions around this state. The model might be unreliable here. So DFS decreases the probability of starting imagination from this transition.
Ah, that's neat. It's like focusing the agent's imagination practice on the parts of the simulation where the simulator itself is likely more grounded in reality based on the training data it's seen.
Precisely. It steers the policy learning towards relying on world model predictions that are more likely to be accurate, which should lead to more stable and effective policy improvement, especially when the model is still rough around the edges early on.
Okay, so we've got the efficient Mamba core and this clever DFS sampling. How did Drama actually do in tests? They used Atari games, right? The standard benchmark.
Yep, they tested it on Atari 100K. That benchmark is specifically designed to measure sample efficiency. You only get 100,000 interactions with the game environment, which isn't very many in RL terms. Performance is typically measured by the score normalized against random play and human performance.
And what were the headline results?
Well, a key finding was about both sample and parameter efficiency. Drama, even a small version called Drama XS, with only about 7 million parameters, which is pretty compact for these kinds of models, achieved a normalized mean score of 105%.
105%. So better than the average human score.
On average, across the tested games, yes. And importantly, this performance was competitive with other state-of-the-art model-based methods like Iris or TWM, which often use much larger models, sometimes significantly larger.
So getting top-tier results with a smaller, more efficient model, that's a really practical advantage.
Absolutely. It makes powerful RL potentially more accessible. They also did a direct head-to-head with Dreamer V3 XS, another well-known model-based agent, matching the model size roughly around 10-12 million parameters.
And
Drama XS came out significantly ahead on Atari 100K. It got that 105% mean score compared to Dreamer V3 XS's 37%. The median scores were also much better for Drama, 27% versus 7%. It really highlights that the architectural choices in Drama seem very effective, even at these smaller scales.
interesting. Did they see any patterns in which games Drama did well or poorly on?
They did. It seemed to excel in games where tracking objects over time or understanding opponent behavior might be important things like boxing, Pong, Asterix, Kroll, and Spackman. The long sequence modeling capability of Mamba likely helps there.
Where did it struggle?
It had more trouble with games requiring very precise pixel-level control, like Breakout or games with extremely sparse rewards, where it's just hard to learn anything meaningful quickly, like James Bond or Private Eye.
Suggest maybe the visual processing part, the VAE, could be an area for future work.
Potentially, yes. Or maybe combining it with better exploration strategies for those sparse reward games. They do briefly show that a better VAE helps, suggesting it's one piece of the puzzle.
Now, good papers don't just show results, they validate why things work. You mentioned ablation studies, testing components in isolation.
Exactly. Crucial for understanding the contributions. First, they tested DFS. Does it actually make a difference compared to just sampling transitions uniformly for imagination?
What did they find?
DFS provided a substantial boost. With DFS, Drama got that 105% mean score. Without it, using uniform sampling, the score dropped to 80%.
Wow, that's a big difference.
It is. DFS really seems to help stabilize and improve learning, especially in games with more complex or changing dynamics. So that validates DFS as a useful technique.
Okay, what else did they ablate? Mamba 1 versus Mamba 2.
Yes, they compared using Mamba 1 versus Mamba 2 as the core sequence model within Drama. Generally, Mamba 2 performed better on the Atari games they tested, which supports their choice to use Mamba 2, even if Mamba 1 might have some theoretical advantages in other contexts.
And the really crucial test for the sequence model itself, handling those long sequences.
Right, this wasn't on Atari, but on a synthetic grid world task designed specifically to require modeling very long dependencies. They compared Mamba, Mamba 2, a GRU, the RNN type, and a transformer.
How do they stack up?
On this long sequence task, both Mamba and Mamba 2 were significantly more accurate. They had lower prediction errors and trained faster than both the GRU and the transformer.
And did the transformer hit that O wall?
It absolutely did. On the longest sequence length they tested, 1,664 steps, the transformer just failed. It ran out of memory on their hardware.
Error, the classic sign.
Exactly. Meanwhile, Mamba and Mamba 2, thanks to their linear OE scaling, handled the 1664 step sequence just fine, no memory issues. It's a very direct demonstration of Mamba's advantage for the kind of long horizon modeling needed for more complex RL tasks.
Okay, so let's kind of zoom out. What are the big picture implications here for you, the listener? What does drama really represent?
I think the main takeaway is that drama demonstrates a practical way to overcome a major scaling bottleneck in model-based RL. By using Mamba, it brings linear complexity, ON, to world modeling, getting past that OL barrier of transformers for long sequences.
And combined with DFS and the parameter efficiency.
Right, combined with the smart sampling of DFS and showing strong results, even with relatively small models, it points towards making sophisticated model-based RL more practical, more accessible, something you could potentially run and train effectively without needing a massive GPU cluster.
It's not like it suddenly solved all of RL, though. They're clear as competitive, but not universally dominant on every single game yet.
No, absolutely. It's highly competitive on the Atari 100 cal benchmark, which is impressive, but there are still challenges, areas where other methods might currently edge it out, and definitely room for improvement.
But that core capability, handling much, much longer sequences efficiently, that feels like the really exciting part for the future, doesn't it? Where could this lead?
I think so too. It's not just about incremental gains on existing benchmarks. The potential to build world models that can efficiently simulate and reason over significantly longer time horizons tasks involving complex planning, maybe learning intricate behaviors, or exploring environments where consequences are very delayed. That's where architectures like Mamba could unlock fundamentally new capabilities that were just computationally infeasible before.
So wrapping up our deep dive today, we've looked at drama, seeing how it uses the Mamba architecture for efficient long-sequence world modeling, and this clever DFS sampling strategy to make policy training more robust. It tackles some key bottlenecks in model-based RL.
Yeah, it makes the whole approach potentially more efficient and accessible, which is a really important direction for the field.
So here's something to think about. We've talked about how quadratic complexity, that recordance, was a kind of hard limit on how far into the future we could realistically simulate within these world models. Now, with linear time models like Mamba breaking that barrier, what kinds of truly complex long-term reasoning or planning tasks, things that need an understanding of consequences, maybe hundreds or thousands of steps away, what kind of AI capabilities might now become reachable by combining these efficient world models with these new, powerful sequence architectures? What new problems can we finally start tackling?